we are ready to speak about product measures. We know now that how to construct a Cartesian product of two sets, of course, and then now we know how to construct a product of sigma algebra. Some people call this a tensor product of these. If you like to be fancy with algebra. And then what about if you have a measure on this sigma algebra mu1, and if you have a measure on that sigma algebra mu2, so what would be the product measure then? How would you define that? Now maybe I don't write any circle here because there's no confusion of what the product means. We need to define a product in some natural way, and the question is how. What is the intuition? Maybe the intuition is here. That again, think about A1 being there and A2 being a set and the other space. Think about a box of this sort again. So what should be the measure of this box? If we have a measure mu1 here and mu2 there. So the measure is somehow, it should be a weighted area. And I think somehow the natural idea is that if you think mu1 gives weight to these sets and the measure mu2 gives weight to these sets here, so then the weighted area of this rectangle here, I think the only natural way to define it should be mu1 of A2 multiplied by mu2 of A2. Yeah. And this is what we want. That's what we want actually kind of our wish somehow is that we want to have a measure on this product space such that mu1 times mu2 of this type of rectangle is equal to the product in this way. Does such a measure exist? Can we do it? And that's the question. Another question is that instead of this this area here, what if instead of a box, so then think about some other set. So instead of a box, so let's say that our set is this one here. Now we ignore this these sets there, and let's say that we want what is the weighted area of this one? Let's call this set A. And that should be somehow, this somehow should be the product measure of mu1 and mu2 of A. But how to define it? Have you seen a definition of this sort before? Maybe you have, well, probably in some previous courses. There are different options. One option is that, okay, we know how to handle these boxes. So maybe we could start filling this with little boxes. Then we try to fill this, let's say, from the inside or from the outside. And then calculate the measure of these boxes and think about, okay, what's the smallest way to fill this from the outside or the biggest way to fill this from the inside. These are called the inner measure and outer measure. And in real analysis, people work on these concepts, and that's one approach. But for probability, that's a bit clumsy one to kind of start filling things. So in a way, the nice kind of definition, this is called called Fubini-Tonelli. Two Italian mathematicians who worked between the First and the Second World War. I think they were active in that time, early 1900. I recall Fubini was let's see, he did a PhD in Pisa, and then I checked that Tonelli worked in Bologna, and they kind of both worked on this construction of this measure. And it's kind of, in some sense, Fubini did the L1 case, kind of. Remember that we can integrate these signed functions, and then we need to restrict that the absolute values are integrable. And Tonelli worked on the positive setting, so in a way, in the positive sense that you might have infinities, but then you don't allow negative functions. So these are the 2 points of view for this theory. So we will learn now Fubini-Tonelli theory, or quite often just Fubini. So what was the construction? As a definition for this product measure, what do we want to do? We want to we follow the Fubini's and Tonelli's approach. Okay, maybe there should be the circle there, but sometimes, yeah, some people use it, some people don't. Let me try to be consistent and not write it now, because I didn't write it there either. And Fubini-Tonelli approach would be that, remember that the measure of a set is also, we learned that it's the integral of the indicator of the set. Let me write this way, that S is the where we integrate, and that was for any set S, that how we define integration, or integral of an indicator. Now we could use this thing to try to define the product measure. And the approach is that let's write down integral of S1 and integral of S2. Let's put the indicator of a set in this, is my point in this set A, or is it not there? So let's put an indicator that our pair of points is in this set A, in the product space. And then we have two variables here. So then think about integrating. First, we use mu2 to integrate with respect to S2. Actually, we need a bit more space. Let me try to be more economical. Let's put it there. And then we make a parenthesis. Think about this way of the integral. And on the other hand, who says that we should first integrate with mu2 and then with mu1? We have 2 different measures. So for this to make sense, that should be the same as we would integrate in the different order. First with S1 of this indicator, and first with measure mu1, and then with measure mu2. Okay, so that's actually what we would like to put as a definition. And in mathematics, whenever somebody gives a definition, we should look, does it make sense? So let's look at this one first. We could think that this integral is actually, now when we think S1 here, think about S1 fixed for a while. Think about that S1 is a constant and we integrate as a function of S2. So can we integrate this? And that's the first question. Is this a measurable when we integrate? And in this sense, the first question is actually that, is this map? Now we use this notation that S2 is mapped into indicator A. S1, S2. Is this measurable? So is this S2 Borel real line measurable? And same thing, of course, is in the second integral. Here we think that S2 is fixed. And in this side, we could think that, okay, it's a function of S1 only. And then we ask, similarly, is the function which maps S1 into indicator A, S1, S2, where now the second coordinate is fixed. Is this S1 Borel R measurable? So these are our questions here. And what should we say about this? It depends on the set A. So what do we assume about set A? We assume that A belongs to. We want to construct a measure in the product sigma algebra S1, S2. So then we assume that A is there. And if I give you any set A, which is in the product sigma algebra, then the question is, then of course, this one is, if you take this pair, now it's mapped into indicator S1, S2. So this one is of course measurable because indicators of measurable sets are measurable. But that does not immediately imply that these other maps are measurable functions. So if you want to be careful, you need to be careful. These are called sections. The answer is luckily yes, they are. The proof is a bit clumsy or technical. You need so-called monotone class theorem. You can check out the lecture notes for details. How to study this? Case one is that you assume that we always first kind of as a sanity check if this should work. We assume the case that A is of the form measurable rectangle. So what then? Then should indicator A, S1, S2 be measurable? So then this is an indicator of a product set. And this was probably in the quiz as well. So for a product set, this indicator means that S1 must be in A1 and S2 must be in A2. So actually we can write this indicator as a product of indicators. So it's a product of this form. And now you think, if you think that you fix, let's say we fix this one. Think about this thing as a function of S2 only. Think about that A2 is a measurable set. So then of course that is measurable. And this is measurable as a function of S2 if S1 is fixed. On the other hand, if we fix S2, and then we think, okay, this is a function only of S1. So then we are looking at actually this is a constant times a function of S1, and then this is a measurable set A1. So again, we have an indicator of a measurable set now in space S1, and that's a measurable thing. So this is the way to check that okay for rectangles or boxes, if we think about that. To generalize from boxes to any sets, the case two, we need to use the monotone class theorem or something of this sort, which is you can check the proof in the lecture notes. Yes, so please let me know if you have questions about this part. So here you need to do reading if you want to really verify this this part. But in the lecture notes, you can find this. So we answer that these are measurable things. So let's clean up a bit. Now we know that if we fix S1 and we think about this as a function of S2, so then it is a non-negative measurable function is in parameter S2. So then we can well define this integral with measure mu2. So this first integral inside is well defined using the machinery of measure theory. What is the outcome of that? It's some number. The outcome of some number which depends now on S1 because we thought that this is a constant. So this outcome is some function. It depends on S1, so we can write that okay, it's something which depends on S1. Then we can think that is a function of S1. Yeah. Same way here. This integral gives us something which depends on S2 because it was considered to be fixed. So then it's something depending on S2. Then we want to integrate with S2 of this. So we are integrating a function S2 which is mapped into this this integral here. Our next question is to check that this definition works. Is that okay? Is this map S1 mapped to this integral S1? Is this measurable function or is it not? And we ask, is this one measurable? And again, it should be S1 to Borel sets measurable, Borel real line. And we ask, is this one S2 Borel real line measurable? The answer again is yes and yes. So yes, it is. Why? A similar technical thing. You can check if A happens to be a nice rectangle first. Let's look. Okay, if we again assume that A1 is a rectangle, so then what should be the integral I1 S1? What should it be in that case? Then we integrate with S2 a rectangle, so we have indicator A1 S1, and remember it factorizes into a product S2 mu 2 S ds2, and then this one is a constant, so it goes to the front by linearity. So this one goes to the front. Then we have an indicator A2 integral with mu2, so we get the measure of mu2 of A2. So the map in terms of S1 is now again S1 maps to this, and here we multiply it by a constant. So again, the same idea. For rectangles, things work well, and both answers are yes, and we check for rectangles in this way. The general case again requires kind of a monotone class argument that yeah, we will skip it for now, and you can check in how to do it in the lecture notes. Do you have questions about checking that these are well-defined things? If no, then we know that here we have a measurable non-negative function. S1 maps to this integral. So then the second integral that we integrate with measure mu1 is well defined. And then we can write that what is here is actually integral S1. And then we have this function I1 S1, which was here. And then we integrate this thing with mu1 measure. That's the way to do it. And here we integrate this with I2 with measure mu2. Are these equal? They should be for this to make sense. Again, if A is a rectangle, what happens? S1, I1, S1, mu1, ds1. We remember what we calculated for this. We remember that it was calculated to be just the indicator A1, S1, and then there was the mu2 measure of A2. That's what we calculated for this I1, and this is what we want to integrate with measure mu1. Here is a constant that goes to the front, so we get the mu2 A2 as a constant to the front by linearity of the integral, and then we are left with the indicator A1 d mu1, which is mu2 A2 times mu1 A1. If you do the same for the second integral, you get the same result. You get mu1 A1 times mu2 A2, so they match. Questions here? No questions. So you can check that, yes, these are okay for rectangles. So this one, okay for rectangles or boxes, as we call them. So for boxes, both are equal to mu1 of A1 times mu2 of A2. Remember that this was actually our wish. If we go back here, we wanted this to be that for rectangles, this is what we want. Now we have checked that, yes, the Fubini-Tonelli definition gives us what we want. For boxes, we get this, which is what we wanted.